Math 1324 for Tuesday, July 26th. We're in the second of 3 days of videos for the second week of working material. And yesterday I planned to try to get around 25, but then my video cut off after problem 23. And that's okay, because 23 times 3 is 69 and there's 70 problems. So as long as we're around 23, 24, or 25 problems a day, we'll make it through. So we'll just pick up where we left off when that video cut off. Okay, so here is the week 2 homework. And I finished through 23, and then I was trying to do 24, but my camera cut off. Okay, so 24. So it gets a little confusing when they have all these symbols inside of here, but again, let's cancel this. In a Venn diagram, if you only have 2 circles, there ends up being 3 sections. The key section is the middle one where they both occur. And you should always start with that one if you're filling out a circle. How many people like chocolate and vanilla ice cream go there? These are the ones that only like chocolate ice cream. They don't like vanilla. And then these only like vanilla, they don't like chocolate. And then you have the outside region for people that don't like either one of those. They like something else or nothing at all. So we're trying to find the number of items. The little n means number of items in A and B. That upside down U symbol is and. And that is something that's told to us. So apparently that's 20. And the reason you want to do that first is that you fill this middle portion of the graph with that first. So put the 20 right here. There's 20 people that like both chocolate and vanilla, for example. So then when they tell you the number of items in A is 30, that's the entire circle A, including these 20 you just put here in the middle. So you have to take the total number in A, 30, minus the 20 you put in the middle, so that way these 2 little sections add up to 30. So that's what this symbol means. This means you're in A and you're not in B, which is just this little moon shape right here. That's 10. And then likewise, there's 70 for all of B, according to this right here, 70 for all of B, but we have that 20 in the middle. So 70 minus 20, that makes 50 that only like vanilla ice cream. That's always how you should fill out one of these Venn diagrams, is you do the middle first, then you take whatever A is told to you as, or if you count it yourself, that minus the middle is the only A's, and then the total number of B's is 70, 70 minus 20, that makes us 50. And then we're also told the number of elements in the entire universe is 100, so we have 100 to work with. And it's not 30 plus 70 is 100, because that's double counting these 20 people. So you want to do 10 plus 20 is 30 plus 50 is 80. We have 80 inside the circles one way or another. There's 100 total in the whole universe. So 100 minus the 80 inside the circles is 20 that are not inside the circles. And that's all the people that don't like chocolate or vanilla. So that's 20. And that's it. There could have been other questions, but the whole purpose of that problem is that's how you fill out a Venn diagram. So you would like to make a salad that consists of lettuce, tomato, cucumber, and onions. You go to the supermarket intending to purchase one variety of each. So here's one of these one of each things. This is different. And you discover there are 9 varieties of lettuce, 5 varieties of tomatoes, 4 varieties of cucumbers, and 4 of onions. How many different salads can you make? This is like my Olive Garden example. So I need to choose 1 of the 9 lettuce, 1 of the 5 tomatoes, 1 of the 4 cucumbers, 1 of the 4 onions. This is the easiest problem you can get. 9 times 5 times 4 times 4. This is the junior high counting technique. 720. That was how Olive Garden, they said they had pastas and sauces and toppings. You just multiply the possibilities. This is not like chocolate and vanilla ice cream where you might like only chocolate, you might like only vanilla, you might like both or neither. That's a different kind of problem. This is I'm doing 1 of each. 1 of each. That's the first thing to look for, is are you doing 1 of each? Using the English alphabet, how many 3-letter character case-sensitive passwords are possible? So passwords, phone numbers, ID numbers, however long the code or the password is, that's how many blanks you want to put. We want a 3-digit password, a 3-code password. And then these always get multiplied together. Because in essence, it's the same deal as the meals. I need 1 of these, I need 1 of these, and I need 1 of these. And it's all about what do you have to choose from. Apparently we're doing English alphabet 3-character sensitive, case sensitive. So that means capital and small case are different. So there's normally 26 letters in the alphabet, but if you use both capital and small letters, then you have to choose 1 of 52 for this slot, 1 of 52, and 1 of 52. There's no restriction about you can't repeat anything. So it's just 52 times 52 times 52. If there were no repeats allowed, then it would go 52, 51, and 50. 52 times 52 times 52 is, see how large this gets, 140,608. That makes it hard for hackers to figure out your password because there's so many cases they'd have to try. 140,608. A small combination lock on a suitcase has 3 wheels, so that's just like 3 slots in a password, each labeled with 10 digits 0 through 9. How many 3-digit combinations are possible if no digit is repeated or if digits can be repeated? So similar deal, except you only can choose 1 of 10 digits. And then if you can't repeat, now you only have 9 left to choose from. And then can't repeat, so now you have 1 of 8 to choose from. Since 9 times 8 is 72, 72 times 10 is 720. If you can repeat, then it's just like this previous problem, 10 times 10 times 10. So there's 1,000 different combinations on one of those locks. Unless you can't repeat, which they let you repeat. They don't put any restrictions on those things when you buy them in the store, but somebody could arbitrarily decide that's what they don't want any repeats. So if no digit is repeated, there's less ways to do it, 720. If you can repeat, then it's 1,000. And then if successive digits must be different, then what happens is, this is kind of like the third case of this. We had one of these yesterday. Then it starts off like part A where you have 10 choices first, but you can't use whatever you got first. But then you could go back to what was first. You just can't go back to what you just put here. So then what happens is, instead of it all being the same, no restrictions are all the same, no repeats, they decrease by 1. And if you can't have 2 in a row that are the same, then only the first time does it decrease by 1. And if there were more slots, I would just have 9999 continuously. So 81 times 10 is 810. So there's really 3 versions of this kind of problem. No restrictions, or no repeats at all, or no repeats more than 2 in a row. But if you did number 7 first, and then you changed to number 2 next, then you could go back to number 7 on the third one. So it's kind of like some repeat is possible, but some repeat isn't. How many different license plates? If you have 3 letters out of the alphabet's 26 and 3 numbers from 0 to 9. And then how many of these license plates contain no repeated letters, no repeated digits? Okay, so this is common. Texas used to have 6 slots on their license plate. Now they have 7 because they were starting to run out. So I just need 3 letters followed by 3 numbers. And now it's actually 4 numbers in Texas. Texas used to be this way. And you just multiply everything together. First, there's no restrictions, so I can pick one of 26 letters for the first slot. And then it's all the same for the letters, since you can have repeats. And 0 through 9 is actually 10 different numbers. So because 1 through 9 is 9, and then you could have a 0. That's 10 different options. No restrictions. Anything's possible. Then you just put 26 every time there's a letter and 10 every time there's a number. So this is what it used to be in Texas. 26 times 26 times 26 times 10 times 10 times 10. We used to have a possibility of 17.5 million license plates in Texas. 17,576,000. They added an extra number. I guess they were getting low on how many possibilities were left. There was getting to be that many cars out there. And some are impossible to get. They're never going to give you things that spell bad words like ASS for the first 3 letters. So all of those combinations or any other thing that might be offensive to somebody, they wouldn't let anybody have that. So 17.5 million is the, in theory, maximum number of cases. But if you add a 4th number, which Texas did, it adds an extra 0 at the end, and it bumps this from 17 million to 175 million. Just by adding 1 extra number now that we have 3 letters and 4 number license plates. If you don't want repeats on either the letters or the numbers, then you go 26, 25, 24, 10, 9, 8. That's part B. Sometimes they would say, so this is all repeats were possible in part A and then no repeats in part B. There could be a part C and a part D where maybe the letters can repeat, but the numbers can't, or vice versa. So you could have like a 26, 25, 24, but then a 10, 10, 10. Or a 26, 26, 26, and a 10, 9, 8. If you let one of them repeat and not the other one. But here it said no repeats on either one of them. So the letters start decreasing by 1, and then the numbers decrease by 1. So then it drops you down to just 11.2 million license plates if you don't want repeats going on. 11,232. This is very similar to passwords or phone numbers. Each slot, you just say how many possibilities do I have, and you multiply them all together. So did I put those answers in yet? No. 17,576, I think I said. Okay, and this was 11,232. A class of 30 music students includes 11 who play the piano, 15 who play guitar, 5 who play both. Okay, how many students play neither? Once you can do both, that's a Venn diagram where the circles overlap. This is like chocolate and vanilla ice cream. So we know that there are, we know that there are 30 total in the whole class. That's the universal size is 30. Number of elements in the whole universe is 30. We have 11 play the piano. So I'll just call that A. 15 play the guitar. But 5 play both. Both is A and B. Notice that this adds up to 31. See how this is already bigger than the whole size? It's because of these 5 people that do both. They're being double counted. So make your circle A, make your circle B. Always put the both in the middle first. There's 5 in the middle. Take the A that's 11, but you have to do 11 minus 5 to figure out this portion here. There's 6 people who only play the piano. They don't play the guitar. And then there's 5 who play the piano and the guitar. That's a total of 11 people who can at least play the piano one way or another. And then likewise, these 15 people, 15 minus 5 gives you 10. 10 of them can only play the guitar. They don't play the piano. But then there's the 5 that play both, so that's a total of 15 people that can play the guitar. So this plus this plus this, that's the total amount of people that are somewhere in the circle. And then if you want neither, neither is the total minus that. 30 minus 21, there's 9 people that play some other instrument or don't play any instrument at all. Well, if they're in this music class, they probably play some other instrument. So they just play something else. So that's how you can always find that. And that's actually how you should build out a Venn diagram, even if you're going to do more to it than that. So 9 people play neither of these 2 instruments. They do something else. A group of 100 touring Europe, 42 speak French, 54 speak Spanish, but some people speak either both or neither. Here it's 19 speak neither. How many people in the group do both? So this is kind of the opposite question of number 29. So we got the 100 total, that's our universe size. We know the 2 A and B numbers, 42 and 54, which is already 96 people. And if you add another 19, you're well over 100. Because you're double counting the ones that do both. The only difference here is this one told us the both and this one tells us the neither. So we have the universe size, I'll just skip right in the end for a minute, is 100. French speakers were 42. Spanish was 54. And then neither was 19. We normally put the both in first, but that's what we're looking for. So this is the unknown this time, so we don't know this middle portion. But 100 minus 19, 100 minus 19, 19 is this outside portion. They speak some other language. They don't speak French or Spanish. So 100 minus 19 is how much total there is in all 3 sections of the circle. Whoops, I wrote the answer. 100 minus 19 is 81. So this plus this plus this has to equal 81. So if I add up what we have so far, 96, it's double counting that middle portion. So if I 42, see how we could do that. X plus something is 42. X plus something is 54. So if I call this X because it's the same for both of them, that plus the only A's has to equal 42. And then X plus the only B's has to equal 54. 42. Maybe that won't help to do that. Okay, so 42 minus X is this, 54 minus X is that. So what if 96, and we need to get it down to 81. What's the difference between 96 and 81? That's 15. So is that 30 maybe? I think you need it twice. So 30. And we could just guess and check here. This is 30. I think that's 30. So then if, let's see if this adds up right or not. Otherwise, maybe it's 15. This needs to be 42, but 42 minus either 30 or 15 would be what's here. So if it's 30, that would make 12. If it's 15, that would make 27. And then B's 54. minus 30 would be 24. I think that's too little. So yeah, I think it is the 15. 54 minus 15 is 39. I just need to know which one of this combination adds up to 81. So is it 27 plus 15 plus 39? Yes, okay. So I had to kind of do that backwards to explain it a little better, so I was wrong at first. So what you do is they told you the neither, so you can definitely subtract that from 100 to see how much these three circles need to add up to. We knew that had to be 81. And then you can add A and B together to see how much over 81 that is. That's 96, but that's double counting those people in the middle. So if you take 96 minus how much you're supposed to have, that's 15 too much. That's the amount in the middle. And then if you take the A minus 15, that gives you 27. The B minus 15 gives you 39. And just as a double check, I added all three of those and it equaled 81. So 27 plus 15 plus 39 plus 19, that would add up to 100. So 15 do both of these languages. 15 people speak both languages. Multilingual, which is very common in Europe and other places around the world because there's a lot of countries near each other and people travel between them a lot, so it just helps to know more languages. Okay, so that was the end of section 7.3. Every section we're doing this week has 10 questions in the homework. So 1 through 10, that was 7.1. 11 through 20 was 7.2. This was logic with those truth tables, and this was set theory. 21 through 30, that was how many ways can you do stuff, or Venn diagrams. So now 31 through 40, this is 7.4, and I can tell what's going on here. Okay, so first I need to teach you how to work these calculations out because you're going to set these up yourself in a minute. So you're going to get a problem where this kind of result occurs, and then the question is how do you simplify it? So what if you have 12, 11, 10, 9, 8 in the top? And then the bottom is 5 all the way down to 1. There's a type of problem where this happens after the first step. So you could do this the slow, painful way, which sometimes gets hard if the numbers are really large, and you could multiply the whole top together with any calculator. But see how large that is, 95,040. You can do the entire denominator together, 120, and divide these two. This is the slow and steady, the hare beats the tortoise beats the hare kind of way. But notice now I got to go back and retype this big number, 95,040 divided by 120. The answer is definitely 792. But what if I did this? What if I said 5 times 2 makes 10? 4 times 3 makes 12. You can often cancel the entire denominator, and ones don't matter in a denominator. So all that's left is 11 times 9 times 8. 11 times 9 times 8 is the exact same answer. That's the easier way to do it. 792. So it's your choice, but anything can cancel with the bottom and the top because there's no addition or subtraction here. So anything you can cancel makes all the numbers smaller and less work to do. Okay, so the denominator of this was 5, 4, 3, 2, 1. That has a special name in math. If you started a number and decreased by 1 all the way down to 1, that's called 5 factorial, and they write it with an exclamation point. So they want me to do 7 factorial next on number 32. That literally means 7 times 6 times 5 times 4 times 3 times 2 times 1. It doesn't have a denominator. So you just use any calculator and keep going. And these get really large too. 70,560. Whoops, where's my, I forgot the number. 70,560. $70,560. It is an integer. Value is an integer. That is weird. Did I type it right? Yes. Oh no, I typed times 14. Exit. I had a typo on my calculator. Maybe you saw it when I was doing it. 7 times 6 times 5 times 4 times 3 times 2 times 1. Somehow I hit times 14. So it wasn't as big as I thought. 5,040. That was just a type. See, that's that one issue when you're doing calculators is sometimes you have a typo and you don't even realize it. There we go. So that's a factorial, that's called. It's part of these formulas we're about to learn. Now this one, the painful way on this one would not be advised. But in theory, you could do 27 factorial with a calculator. But it's such a ginormous number that you won't even be able to write it down. And then 24 factorial in the denominator. Those are both of those are ginormous numbers. They're bigger than the number of stars in the universe. It's crazy big how these get. But luckily you don't need to do it all the way down to the bottom, because not only is it way too big, it takes a long time too. Because 27 factorial goes like this, and then I'm just going to put ... all the way down to 1. And then because there's a denominator, the last problem didn't have a denominator, but this one does, 24, 23, all the way down to 1. And it's all multiplied and divided. There's no addition or subtraction. So you can cancel anything in the bottom that's similar to anything in the top. Even when I was canceling here, I didn't have to do 5 times 2 is 10. I could have just went 5 goes into 10 twice. You can do that too. But sometimes you literally have 24 cancels 24 and 23 would cancel 23. In other words, 24 down to 1 here entirely cancels 24 down to 1 there. The entire bottom knocks out most of the top. All that's left are these 3 numbers. So it's much quicker to do 27, 26, 25, and you're done. And if you wanted to do 27, 26, 25, 24, all the way down to 1, not only does that take a long time, it's so large that it's going to display the answer on your calculator as scientific notation. And you wouldn't be able to write it down to then do the other half of the problem and then divide the 2. So it just becomes an impossible task to do this as is, even with a calculator. So you really need to know that shortcut way of canceling to finish this problem. 17,550, which is an integer. Did it again, okay. Oh, I didn't, I just assumed it was the same order as last time. See, I remember I said it is an integer, but this says it's not an integer, so I guess they flip-flop that every so often to see if you're paying attention, because I wasn't. Whoops. Oh, 550, not 750. So now I misremembered what the answer was. There we go. So these are just little careless errors that anybody can make, and unfortunately that is frustrating when you're taking a test and you lose points just because of careless mistakes. But it happens to everybody. Okay, so this is part of a formula that I guess they're going to get to eventually, but they're teaching you first how to simplify these. But concepts coming up soon, we're going to have 14 factorial over 2 factorial, and then you do 14 minus 2 factorial. So the bigger factorials in the top, the smaller ones in the bottom, and then you subtract the 2 in the bottom also. But go ahead and do this in your head. What's 14 minus 2? 14 minus 2 is 12. So that makes it look easier or simpler this way. Always do that. Never leave this like this. And then now you can sort of do what we did on that previous problem. 14 factorial, you don't need to do the whole thing. Just get the pattern going and put ... down to 1. The 2 factorial is just 2 times 1. And then you got 12 factorial, which if you notice right here, it's going to match the top. That portion matches the top. So the 12 factorial from the denominator cancels out most of the numerator. And a 1 in a denominator doesn't matter. 2 can go into 14 7 times. But after I canceled all this down, you could, in theory, in your calculator, do 14 times 13, write it down. 2 times 1 is 2, and then divide by 2. 14 times 13, and then divide by 2, and the answer is 91. But I would just do 7 times 13 and get there quicker. 91. So the value is an integer. Integer means it's an exact number. It's not a decimal or a fraction. 91s, you got to pay attention to where they put, they apparently move. I was assuming they always put integer first, but they caught me on the last problem. I wasn't paying attention. Okay, well, here's again, this is so large you could never write this number down. It would take you hours to type it into a calculator anyway. So you really need a shortcut here. 600 factorial divided by 598 factorial. Oops. Most of it cancels. Luckily, otherwise we'd be here all day. 600 factorial divided by 598 factorial. 600 factorial is 600 times 599 times 598 times 597 all the way down to 1, which is a long, long, long way down to 1. There's 600 numbers there. It would be hard to just write that out without even calculating it. It would run off the paper after a while. But luckily, the bottom is 598 factorial. So the entire bottom cancels with all but 2 numbers in the top. And unlike the previous problem, we don't have this extra 2 factorial here. So there's nothing left in the bottom. So you don't have to divide anything. It's just 600 times 599, and you're done that quick, even though that alone is very large. 359, 400. $359,400, and it is an integer, no decimal or fraction. Okay, so this is why they've been doing that the first 5 problems of this section. Here's the concept, one of the 2 concepts here. So let me go back to, there's 3 major types of how many ways can you do something. The first one was taught last section, and the other 2 are going to be taught now. These other 2 are similar to each other. The first one is when you choose one of these and one of those and so on. Like Olive Garden, choose one of 5 pastas and choose one of 6 sauces and choose one of 7 toppings. Anytime you have a series of 2 or more decisions and you want to do one of these, one of these, one of these over and over again. That's the junior high kind where you just multiply all the numbers together. That was taught in the previous section. Now in this section, there's 2 kinds. One's called a permutation, and the other one's called a combination. And it's written either 9P2 or 9C2. You always put the bigger number first, smaller number last, even if it's worded backwards, and then P for permutation, C for combination. Permutation, order matters. Combination, it doesn't. Or the objects are treated differently, whether they're different or the same, and in a combination, objects are treated the same. And what's different here is you're not doing one of these, one of these, one of these. It's not 1 of 9 and 1 of 2. If it was 1 of 9 and 1 of 2, then you would do 9 times 2. These answers are not going to be 9 times 2, though. This is where you're choosing, in both scenarios, you're choosing 2 out of 9. I've got a club of 9 people, and I want to choose 2 of them out of the 9 to be officers of the club. then that's a combination, because officers, I'm treating them the same way. Their jobs are the same. So then order doesn't matter. It doesn't matter who's first, who's second. They both get the job. But if I choose 2 out of 9 people in a club and one's going to be president and the other one's going to be vice president, now their jobs are different. And the president's, in theory, more important and has more power. So try telling Donald Trump that he has to be vice president today. He would probably throw a fit. So 9 combination 2, 9 permutation 2. These are done very similarly. And then the only difference is order matter or not. That's hard to tell sometimes. Or are the objects treated differently or not? If it's 9 permutation 2, what you end up doing is 9 factorial over 9 minus 2 factorial. If it's a combination, it's 9 factorial over 2 factorial and 9 minus 2. These are done very similar to each other. And then there's even shortcuts to this that you don't have to do these like we were doing a second ago. So if you get a permutation, you start at 9. You start decreasing by 1, multiplied together until you have this many numbers. Because this is going to be 7 right here, and the 7 factorial is going to knock out 7 down to 1 in the top, leaving only 9 and 8. But the shortcut is if you get, say, 13